Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. So today, we are going to discuss about the convolution theorems and correlation concept. In the yesterday class, we completed the concept of convolution and some properties of convolution, and some few examples also we did. And today we are going to discuss about the convolution theorems and the concept of correlation. So the convolution theorem. So convolution of signals may be done either in time domain or frequency domain. Time domain or the frequency domain. Time domain means it's a continuous time function. The frequency domain means it is in the discrete time function. The formula is the y of t is equal to x of t, the convolution of h of t as the time domain function. Time domain, and y of n is equal to the convolution of x of n with h of n. It's a frequency domain function. Okay, convolution of signals may be either in the time domain or in the frequency domain. So they are following two theorems of convolution associated with the Fourier transform: time convolution theorem and the frequency convolution theorem. Now the time convolution theorem. The first one, the time convolution theorem states that the convolution time domain is equivalent to multiplication of their spectrum. So we already know this is one of the property of convolution time domain of the Fourier transformation. The statement is x1 of t is x1 of omega, x2 of t is x2 of omega. The convolution of x1 and x2, x1 of omega and x2 of omega. Let's take the proof. Apply the Fourier transformation on both sides. The integral minus infinite to infinite x1 of t and x2 of t e power minus j omega t dt. Okay, here the t is there, my dear students. So actually we know the formula of the x1 of t and x2 of t is the integral minus infinite to infinite x1 of tau and x2 of t minus tau theta. Substitute this is as a convolution of the two signals. Let in the RHS integral minus infinite to infinite and another integral x1 of tau x2 of t minus tau d tau e power minus j omega t dt. Okay. Take t terms all in the one side. The integral minus infinite to infinite x2 of t minus tau e power minus j omega t dt, and the d tau is already we have in this convolution formula, and x1 of tau. Using this time shift property, we know directly how to write it as x2 of omega into e power minus j omega tau. Otherwise, t minus tau is equal to, assume the p, and t is equal to p plus tau, dt is equal to dp, or t minus tau is equal to m. Consider it as. Okay, so Fourier transformation of the time domain function is equal to integral minus infinite to infinite x1 of tau, integral minus infinite to infinite x2 of p, because it is a t minus tau is a p, e power minus j omega t as p plus tau dp and the d tau. The x1 of tau and the x2 of p e power minus j omega p dp, and you can separate the exponential value, the e power minus j omega tau d tau. So within the parentheses we here, it is in the form of the Fourier transformation definition. Since it is x2 of p, you can write as a x2 of omega. Already we have the x1 of tau e power minus j omega tau d tau. It is also the definition of the Fourier transformation. So it is x1 of tau, write it as x1 of omega and x2 of omega. The convolution time domain product in the frequency domain function. This is a time convolution theorem. Time convolution theorem. Already we know one of the property of Fourier transformation, convolution in time domain. Convolution in time domain function. Now the frequency convolution theorem. Frequency convolution theorem. The frequency convolution theorem states that the multiplication of two functions in time domain is equivalent to the convolution of their spectrum in the frequency domain. Mathematically, it is frequency domain function. See, I told that it is a y of n is equal to x1 and x2. It is not that one. It is the multiplication theorem, or the multiplication or the modulation theorem, my dear students. These also we already seen the one of the property of the Fourier transformation. The product in the time domain, convolution in the frequency domain with the 1 by 2 pi. Convolution with of 2 pi. The Fourier transformation you can see. The Fourier transformation of x1 and the x2. Okay, here now I'm taking the frequency convolution theorem, or it also called it as a modulation theorem, it's a multiplication theorem. X1 and x2. So x1 I replace with the inverse Fourier transformation. The inverse Fourier transformation formula is 1 by 2 pi integral minus infinite to infinite x1 of lambda e power j lambda into t d lambda. Okay, my dear friends, is a positive exponential x2 of t and e power minus j omega t dt. So don't write here the j omega t and here also the j omega t. Now, to avoid the ambiguity here, to get it is a e power 0 is a 1 value. We can't do continuation for the design without any exponential values. So, change is x1 of lambda and e power j lambda into t d lambda. So, with respect to the lambda, because it is an inverse Fourier transformation, actually it is a d omega, so frequency. So now I interchange the order of the integration here, 1 by 2 pi x1 of tau, you can write this outside, and the t functions is in the one parenthesis, integral minus infinite infinite x2 of t e power minus j omega t e power j lambda into t dt and the d lambda. So basis of the same, you can add the powers here, integral minus infinite infinite x2 of t e power minus j omega, and it is a plus. So take the minus into minus is a plus, e power j minus j omega minus lambda into tau dt. Lambda into t minus, it's not the tau, it is t dt. Now we got the frequency shift property. Actually, the Fourier transformation definition saying that x of t e power minus j omega t dt. Instead of omega, here the omega minus lambda. So x2 of omega minus lambda by using frequency shift property. So 1 by 2 pi integral minus infinite infinite x1 of lambda x2 of omega minus lambda into d lambda. Okay, my dear students. Now again, you can see the integral minus infinite infinite x1 of lambda x2 of omega minus lambda d lambda is a convolution formula. x1 of tau x2 of t minus tau d tau. x1 of tau x2 of t minus tau d tau is equal to y of t. Okay, y of t. Nothing but here I am taking that x1 of omega with the convolution of x2 of omega. Y of omega is nothing but. So the product of the time domain function will get the convolution in time domain frequency domain with of 2 pi. Okay, or otherwise the 2 pi x1 of t, x2 of t is a Fourier transformation is a x1 of omega with the convolution of x2 of omega. Or otherwise, this frequency convolution theorem in radian frequency. This is angular frequency here. The radian frequency, the same thing. Change it is omega as a 2 pi omega f and 2 pi f. Shortcut notation you can write as x1 of f and the x2 of f. So these two theorems we already seen in the We already discussed in the Fourier transformation, my dear students. We already discussed in the Fourier transformation properties. That is, one is convolution time domain, and the second one, the frequency convolution theorem, is a modulation theorem or the multiplication theorem, my dear students. So take some examples on this. Find the convolution of the signals x1 of t, x2 of t using Fourier transformation. Using the Fourier transformation means using the convolution theorem. Simply saying using the convolution theorem. So x1 of t e power minus at mu of t, the time domain function is given, and x2 of t is also the time domain function. The Fourier, we have to find out the convolution in the time domain to get the product in the frequency domain. So what is the x1 of t, the Fourier transformation? We already know the e power minus at mu of t is 1 by a plus j omega. E power minus bt mu of t is 1 by b plus j omega. Now you can multiply the two functions according to the Fourier transformation of the convolution of the two time domain signals. So x1 of omega and x2 of omega. It is a Fourier transformation. Correct. Now the product is a 1 by a plus j omega by the into 1 by b plus j omega. You take it as inverse Fourier transformation of this function. Then only you get the convolution of x1 of t and the x2 of t. Okay. So x1 of t, x2 of t is the inverse Fourier transformation of 1 by a plus j omega, b plus j omega is equal to. You take the common as 1 by b minus a, the inverse Fourier transformation. How we get this one? By using partial differentiation. So I will explain clearly. So example is given. You have to find out the convolution for the given x1 of t is equal to e power minus at mu of t, and x2 of t given is e power minus bt mu of t. Find the convolution x1 of t with the convolution of x2 of t using convolution time theorem. Using convolution time theorem, or directly you can find out by using substituting the formula itself, my dear students. Yesterday we did some examples by using the convolution formula, but here you have to use the property using the convolution theorem. Okay. So what is the Fourier transformation of the signal x1 of t is a e power minus at mu of t. x1 of omega is equal to 1 by a plus j omega, and x2 of t given the e power minus bt mu of t. x1 of x2, my dear students, x2 of omega is equal to 1 by b plus j omega, 1 by b plus j omega. Now the Fourier transformation of x1 of t with the convolution of x2 of t is equal to x1 of omega into x2 of omega. So what we got, x1 of and x2, 1 by a plus j omega into b plus j omega. But I need the x1 of t with the convolution of x2 of t. Take this Fourier transformation as inverse Fourier transformation. Okay, so x1 of t with the convolution of x2 of t in the time domain function. How we get it is the inverse Fourier transformation by using the inverse Fourier transformation of a by a plus j omega plus b by, not the b, okay, capital B by the small b into j omega. Now you can find out a and the b values. So what is the a? Comparing the 1 is equal to a into b plus j omega plus b into a plus j omega to find out the capital A and the capital B. Substitute a is equal to minus j omega, a is equal to minus j omega. Here the b term is a 0, not the a is equal to minus j omega is equal to minus a. J omega is equal to minus a minus 1. So b minus a. Therefore, a is equal to 1 by b minus a. Okay. We got the a is 1 by b minus a. Similarly, to find the b value, substitute j omega is equal to minus b. Substitute j omega is equal to minus b. So 1 is equal to b into j omega is equal to minus b. Here it is a minus b. So b is equal to, now it is in the b minus a. Now change this also the b minus a minus 1 by b minus a. We got the b is equal to minus 1 by b minus a. Okay. So the x1 of t, convolution of x2 of t is equal to a is 1 by b minus a whole divided by a plus j omega. So b is 1 by b minus a whole divided by b minus b plus j omega. It is a Fourier inverse Fourier transformation you can apply here. The inverse Fourier transformation f inverse. Okay, that is equal to the both having 1 by b minus a is a common. What is the inverse Fourier transformation of 1 by a plus j omega? The inverse Fourier transformation of 1 by a plus j omega minus inverse Fourier transformation of 1 by b plus j omega. Okay, my dear students. So that is equal to 1 by b minus a is a Fourier inverse Fourier transformation of a plus j omega. We know the e power minus at mu of t minus here the e power minus bt mu of t. Okay. Therefore, the convolution of the given the two signals x1 of t and the x2 of t is equal to, take a 1 by b minus a e power minus at minus e power minus bt into mu of t. Okay, my dear students. So note down when I am explaining in the whiteboard, my dear students. Otherwise, you can take the screenshots. So better for that. I can see here the same thing. We'll got the 1 by b minus a e power minus at mu of t minus e power minus bt mu of t. So this is, we did this in the without using the formula, by using the theorem. The theorem is a convolution in time domain. Okay. The next example. So next example, you can see here the find the convolution of the signals x1 of t is equal to 2 into e power minus 2t mu of t, x2 of t is a mu of t using the Fourier transform. And simply saying that it is using the property, Fourier transformation property. So x1 of t is a 2 into e power minus 2t mu of t. x1 of omega is 2 is a constant e power minus 2t mu of t, we know the a plus j omega, 2 plus j omega. Mu of t See, remember here, the mu of t, the Fourier transformation is mu of t, the Fourier transformation is pi into delta omega plus 1 by j omega minus 20. So remember this one. The mu of t, the Fourier transformation is, how we got this one? Signum of t is equal to 2 into mu of t minus 1. Okay. Signum of t plus 1 by 2 is equal to mu of t. Okay. The Fourier transformation of mu of t is equal to 1 by 2 plus 1 by 2 signum of t. Okay. Now, what is the Fourier transformation of 1? 1 Fourier transformation is 2 pi into delta omega. Okay. 1 by 2, the Fourier transformation is pi into delta of omega. So, the Fourier transformation of 1 by 2 is mu of t. The Fourier transformation is pi into delta of omega. Is a Fourier transformation. And here, the signum of t. Signum of t Fourier transformation is 2 by j omega. Now the signum of t by 2, the Fourier transformation is 1 by j omega. Okay, everything we know, my dear students. 1 by 2 signum of t is 1 by j omega. Now, what is the Fourier transformation of mu of t? Pi into delta of omega plus 1 by j omega. This is a formula for the signum of t. From this formula, the condition, the Fourier transformation of mu of t we got as a pi delta omega plus 1 by j omega. Okay, so that only I wrote here. They wrote here the x2 of omega is equal to pi delta omega plus 1 by j omega. So by using the Fourier transformation, you have to find out the convolution here. Multiply the two functions, 2 by j omega plus 2 into pi delta omega plus 1 by j omega. Multiply the 2 j omega by 2 by j omega into 2 plus j omega plus 2 pi delta omega j omega plus 2. Now inverse Fourier transformation. The inverse Fourier transformation here, you write as a 2 by j omega plus 2. The second term is there. The 2 we can write it as 1 by j omega minus 1 by j omega plus 2. How it is? That is a multiply of j omega plus 2 minus j omega plus 2 minus j omega. Okay, so simply the denominator will get as a 2, j omega get cancelled, and same thing will get 2 by j omega and j omega plus 2. You see here the 2 by j omega and j omega plus 2 can write as a by something or b by something. A is 1 and the b is a minus 1 by using the partial fractions only. Otherwise, a 1 by j omega, you got the 1 minus j omega plus 2. So see here, take the cross multiply the j omega plus 2 minus j omega by j omega into j omega plus 2 minus 2. So j omega get cancelled, 2 by 1. Same thing. You got the three terms. The delta omega, since the delta omega is equal to 1 for omega is equal to 0 and delta omega is equal to 0 for omega not equal to 0, we have 2 pi delta omega is equal to 2 pi delta omega by the j omega plus 2 is equal to pi into delta omega 1. Why it is, you see, here the omega term is delta omega is equal to 1 for omega is equal to 0. You see the 0 substitute here, then only the delta omega is equal to 1. The 2 pi delta omega by the j omega plus 2. We know the delta omega varies only at 1 omega is equal to 0. Is equal to 0 when omega not equal to 0. Now I am substituting the omega is equal to 0 here in this function. What is it? 2 pi delta of omega, nothing but it is a 1, and j omega is a 0 plus 2. So 0 plus 2 means get cancelled. It's a pi into delta omega. And omega is not equal to 0. When omega is not equal to 0 means the value is a 0 here. 0 means entire the term function is a 0. Following my students. So replace the 2 pi delta omega j omega plus 2 as pi delta omega only. This is the condition here. You see this one. Delta omega is equal to 1 for omega is equal to 0, and delta omega is equal to 0 for omega not equal to 0. This is a impulse function standard signal. Okay. Now we got the 1 by j omega minus 1 by j omega plus 2 plus pi into delta omega. Pi into delta omega. See, there is a remaining is not there here in this slide. I will explain. Now with the Fourier, inverse Fourier transformation of 1 by j omega, we need to find the x1 of t with the convolution of x2 of t is equal to, what is the inverse Fourier transformation of 1 by j omega plus 1 actually? 1 by a plus j omega. So e power 0 into t mu of t. Okay, my dear friends. The plus 0 is already there. Minus 1 by j omega plus 2 means e power a term is minus 2t mu of t. Okay. Plus pi into delta omega. Pi into delta omega. That is the inverse Fourier transformation. Inverse Fourier transformation of pi delta omega. So one Fourier transformation is 2 pi delta omega, and 1 by 2 the Fourier transformation is pi into delta omega. What is a pi delta omega? Inverse Fourier transformation is 1 by 2 minus 1 by 2. Okay. Now we got x1 of t with the convolution of x2 of t is mu of e power 0 is a 1. So mu of t minus e power minus 2t mu of t plus 1 by 2. Okay. This is the final answer for this example, my dear students. So the convolution of the given two signals is 1 by 2 plus mu of t minus e power minus 2t mu of t. Got it? Now the next topic, signal comparison or the correlation of functions. This is actually as per your syllabus, my dear students. What I explained the last class and the today's class, up to the convolution theorems and examples, that you have to learn when you have to learn the correlation function. So without knowing the convolution, it is somewhat difficult to understand the correlation of the functions, my students. So definitely there is a relation between of the convolution and the correlation, the formula wise and the concept wise also. Now what is the concept you have to see here? The both are the same. Concept of the correlation, the signals may be compared on the basis of similarity of waveforms. The signals may be compared on the basis of similarity of waveforms. Quantitatively, a comparison may be based on the amount of component of one waveform contained in the other waveform. The similarities, the amount of component of one waveform contained in the other waveform. what are the similarities are there in the two signals. Whether the two signals are the different signals, we call it as a cross correlation. Whether these two signals are the same signals or itself we are comparing, that we can call it as a autocorrelation function. If x1 of t and x2 of t the two waveforms, then the waveform x1 of t contains an amount of C12 of x2 of t of the particular waveform x2 of t in the interval t1 and t2, where this is a formula we already seen, my dear students. So this is a formula for the orthogonality function. Orthogonality function, the approximation signal of orthogonality. But they are saying that Cn is equal to integral t1 to t2 x1 of t x2 of t dt and integral t1 to t2 x2 square of t dt. Actually, it is a f of t xn of t, xn of t and xn square of t. Here the 2 is the second signal, and taking here also the xn square means x2 square of t dt. The magnitude of integral in the numerator might be taken as an indication of similarity. If this integral vanishes, that is integral t1 to t2 x1 of t x2 of t dt is equal to 0, then the two signals have no similarity over the interval of t1 and t2. If both are orthogonal, mutually perpendicular to each other, both they are not similar. So one is in the y-axis and another one is a x-axis. When the numerator get it is the integral is a 0 with the interval of t1 and t2, such signals are said to be the orthogonal. See, my dear students, and the two signals have no similarity over the interval t1 to t2, such signals are said to be orthogonal over the specified interval. Okay, we already learned in the first unit itself, my dear students. Then the integral t1 to t2 x1 of t x2 of t dt forms the basis of comparison of the two signals x1 of t and the x2 of t over the interval of t1 to t2. In general, in comparing the two signals over the interval minus infinite to infinite, so the integral becomes minus infinite to infinite. Here the minus infinite is there, minus students. Minus infinite to infinite x1 of t x2 of t dt. Correlation, nothing but comparison. Similarities we have to see in that two signals. For that, you have to take the mathematical equation as integral minus infinite to infinite x1 of t x2 of t dt. If it is a 0, both are not having any similarities, and they are calling it as a orthogonal functions. Okay. Now, however, there is a difficulty with this test integral, which can be illustrated with an example, a radar pulse. Figure shown here, the radar pulse shows as a transmitted pulse and a received pulse which is delayed. See, actually, this is a signal, my dear students. We started at the 0, a sinusoidal signal x1 of t, and at the received pulse, transmitted pulse is a x1 of t here, and a received pulse which is delayed with respect to the transmitted pulse by the t seconds. See, after the t seconds, see here it is a t. Delay function means, let us say, the unit step function is like this. With the t delay functions means it starts from the t samples. Okay, my dear student. Similar way with the t delay samples, which is a delay with respect to the transmitted pulse by t seconds, obviously the two waveforms are identical except that one is delayed with respect to the other. The same signal is getting in the transmitted side what we send, and the received is also the same, which is a ripple curve. We can call it as identical replica function. But after the delay, it is received at the receiver side. The only the difference is that, okay, obviously the two waveforms are identical, except that one is delayed with respect to the other. At the test integral minus infinite to infinite, x1 of t, x2 of t dt yields 0 because the product x1 of t and x2 of t is 0 everywhere. This indicates that the two waveforms have no measure of similarity. If they get it is a 0, which is obviously a wrong conclusion. Hence, in order to search for a similarity between the two waveforms, we must shift one waveform with respect to the other waveform by various amounts and see whether the similarity exists for some amount of shift on the one function with respect to the other. That shift you can take it as x2 of t minus tau into dt, my students. Okay, what they're explaining that if the two signals have measure the similarities in that waveform, if there is no any delay, if that becomes obviously it is a 0, there is no any similarities between the two signals. For that, what we have to do, for the similarities between the two waveforms, we must shift one waveform with respect to the other. One waveform in the two signals, either x1 or the x2. One waveform is shifted to the other waveform by various amounts to see whether the similarity exists for some amount of shift of one function with respect to the other. So, therefore, the test integral is modified as integral minus infinite to infinite x1 of t, x2 of t minus tau dt. x1 of t, x2 of t minus tau dt. The second signal I shifted here with the tau samples. So where the tau is searching or scanning parameter. This integral is a function of tau. This integral is known as cross correlation function between x1 of t and the x2 of t. Why I am saying it is a cross correlation, my dear students? Because these are the two different signals. Cross correlation between x1 of t and x2 of t. It is denoted by R12 of tau. R12 of tau. It is immaterial whether we shift the function x1 of t by an amount of tau in negative direction or the shift the function x2 of t by the same amount in the positive direction also. Both the resultant will be the same. So here I am taking the x2 and it is shifted in the right side because it's a delay function. I am taking the another one, the x1 of t is a delayed, but it is not in the positive direction, it is in the negative direction shift. So advanced function. So x1 of t plus tau, x2 of t dt is equal to R12 of tau. So both are the same, my dear students. It is also equivalent to integral minus infinite to infinite x1 of t on signal. What we are saying, the second signal you have to shift x2 of t minus tau dt. Here I am taking the negative x1 of t by the amount of tau in the positive negative direction, or the shift of function x2 of t in the same amount in the positive direction. This is a positive direction, students. Delay function, and in this function, negative values means it is in the towards the left side, and this is the towards the right side function. Okay, both the resultant value is the same. Thus, the correlation of two functions or signals or waveforms is a measure of similarity between those signals. Similarities between those signals. The correlation is of two types. Correlation of two types, cross correlation and autocorrelation. The autocorrelation and cross correlation are defined separately for energy or periodic signal, energy signals, and the power signals. So both are periodic signals only, my students. The correlation of two types is a cross correlation and autocorrelation. The autocorrelation and the cross correlation are defined separately for energy signals and the power signals. Energy signals and the power signals, my students. Okay. Once again, I will explain what is the concept of the correlation means. So we take the one of the equation we already know at the orthogonality of approximation signal equation. That is a Cn actually. Now I have taken the two different signals, C1 to integral T1 to T2 x1 of t, x2 of t dt, and integral in T1 to T2 x2 square of t dt. And the numerator integral vanishes. There is no any similarities between the two signals. We can call it as orthogonal. But to compare the two signals over the interval of minus infinite to infinite, take the test integral becomes is minus infinite to infinite, x1 of t and x2 of t. Okay. However, there is a difficulty with the test integral, which can be illustrated with the example of radar pulse. As a transmitted pulse and received pulse, which is delayed with respect to the transmitted, means identical function you have to get, but it is received with some delay at the receiver side. So obviously the two waveforms are identical except one is delayed with respect to the other. So with that, you can write it or you can modify the equation as integral minus infinite to infinite, x1 of t, x2 of t minus tau dt. As in it moves in the positive direction, or otherwise it moves in the negative direction also, any one of the signal. Integral minus infinite to infinite, x1 of t plus tau, x2 of t dt. Here the dt, my students. So the correlation function or cross correlation function is denoted by R12 of tau. R12 of tau. Autocorrelation simply R11 of tau. Because the signals itself signal, here the two different signals are there, x1 and x2. Autocorrelation means same signal, R of tau or R11 of tau. Follow my students. And these are correlation functions of the two types, cross correlation and autocorrelation, and is also separately defined for energy and the power signals. Both are the periodic only, my students. Both are periodic. First, we have to go to the discussion about the cross correlation. The cross correlation between the two different waveforms of the signals is a measure of similarity or match or relatedness or coherence between one signal and the time delayed version of another signal. So everything is the same idea. Either it is a similarity you have to see, or it is a match or not, relatedness or coherence between one signal and the time delayed version of another signal. See here, the one signal with the time delayed of one other signal. That means the cross correlation between the two signals indicates how much one signal is related to the time delayed version of another signal. What it means? The cross correlation between the two signals indicates how much one signal is related to the time delayed version of another signal. Time delayed version of another signal. The cross correlation of energy signals. See, my dear students, the cross correlation is defined separately for the energy and the power. Cross correlation of energy signals. Consider the two general complex signals x1 and x2 of finite energy. The cross correlation of these two energy signals is denoted as R12 of tau is given by integral minus infinite infinite x1 of t x2 star. Why we wrote that this is star? If both are identical, we know the x1 of t and x2 star of t is a squared magnitude energy signal. Okay, you can take any one signal is a complex. So x2 star, or it is also equivalent to the negative of taus, negative of or negative values of the tau function, means towards the left hand side, the advanced function. Integral minus infinite infinite x1 of t plus tau x2 star of t dt. If two signals x1 of t, x2 of t are real, R12 of tau is equal to integral minus infinite infinite x1 of t, x2 of t minus tau dt. The delayed function, advanced and the delayed functions. Okay. And these two are the complex function, and here the two signals are the real, x1 and x2, but here it is a one real and the complex. If x1 of t and x2 of t have some similarity, then the cross correlation R12 of tau will have some finite value over the range of the tau. Also, if integral minus infinite infinite x1 of t x2 star of t dt is equal to 0, that is R12 of 0 is equal to 0, then the two signals x1 of t x2 of t are called as orthogonal signals. We know that the numerator becomes a 0, means definitely that is a orthogonal signal only. That is, the cross correlation for orthogonal signals is a 0. Cross correlation of orthogonal signals is a 0. R12 of 0 is equal to the 0 only. R12 of 0 is equal to 0. Following my dear students. How it is simply saying that here the tau is equal to 0, it becomes of x1 of t and x2 star of t dt. Tau is equal to 0. So R1 to tau here, the tau 0, the value is a 0. So definitely this function becomes a 0. The cross correlation function is orthogonal signals is a 0 minus 1. Another form of cross correlation between x1 of t and x2 of t is R21 of tau, interchanging 2-1 of tau. So 2 I am taking here and the 1 is here. x2 of t, x1 star of t minus tau dt. Okay. In the above equation, the cross correlation function R12 of tau is a function of the variable tau. The variable tau is called a delayed parameter or scanning parameter or setching parameter. It is a time delay or time shift of one of the two signals. The delay parameter tau determines the correlation between the two signals. Two signals with no cross correlation at tau is equal to 0 can have significant cross correlation by adjusting the parameter the tau. Two signals for which the cross correlation is a 0 for all the values of the tau are called uncorrelated or incoherent signals. Incoherent signals. Coherent signals means they are cross correlation, similarity, relatedness, identical, or coherence. But there is no any similarity of these two signals. When the tau is equal to 0, the R12 of tau is equal to 0. That call it as the cross correlation is 0 for all the values of tau are called incorrelated or incoherent signals. Coherent signals means they are identical. Incoherent signals means they are not having any identicals. Simply they are orthogonal to each other. 0 R12 of tau is equal to 0 and tau is equal to 0. Following my dear students. Now see some properties of cross correlation function of energy signals. The following are the properties of cross correlation of energy signals. The cross correlation function exhibits a conjugate symmetry. Conjugate symmetry R12 of tau is equal to R21 star of minus tau. That is, unlike convolution, cross correlation is not in general commutative. Unlike convolution, cross correlation is not in general commutative. Following my dear students. Actually, the convolution is a commutative property, saying that it is interchanging also. But here, when we are interchanging R12 of tau as a 212 of star, the tau is becomes of minus, then only both are equal. It is R12 of tau is R21 of tau here. It is not the minus, it is a plus. It is a tau. It is not equal. Okay, my dear students, it is not equal. Now, let us see that some ambiguity we got, I think. What is the formula here? R12 of tau is equal to integral minus infinity infinite x1 of t x2 star of t minus tau dt. Okay. Now, whenever it is interchanges the value of x2 and x1 here. And what is the R21 of tau is equal to integral minus infinity infinite x2 of t and x1 of t minus tau dt as a conjugate. Following my dear students. Now, I'm changing it as or the star, you can write here the conjugate value. So take this as a star. Now R1 of tau is equal to, when it is both are equal, R21 of, take this as a minus tau. Tau as a minus, integral minus infinity infinite, x2 of t, x1 of t minus of minus, it becomes of a plus dt. So now you can see here is a delayed function, and another one is a advanced function xt plus tau, both are equal. So R12 of tau is equal to R21 of minus tau, my students. Okay. Then only these both are equal, otherwise it is a not equal, becomes R12 of tau is equal to 0. So tau is equal to 0, it becomes of x1 t, x2 star of t, and tau is equal to 0, x1 t and x2 star of t. That value is a convolution function. That convolution definitely it becomes, it's a 0 value. So R12 of 0 is a 0 value. The tau is equal to 0. That is the second one. R1 to the second property. The first property only when we are changing this 1 2 to the 2 1. Unlike the convolution, correlation is not obeys the commutative property, not in general a commutative. Okay. And the second property saying that if R12 of 0 is equal to 0, that is integral minus infinity infinite x1 of t, x2 star of t dt, and tau is equal to 0. Either you can substitute in the plus value and it is a minus value, minus students. In both the cases, it becomes of x1 and x2 only. Okay. So x1 of t and x2 star of t dt is equal to 0. Then the two signals are said to be orthogonal over the entire time interval. Over the entire time interval. That becomes of energy signal E is equal. Okay. Energy signal E is equal. And third one, the cross correlation of two energy signals corresponds to the The cross correlation of two energy signals corresponds to the multiplication of their Fourier transformation of one signal by the complex conjugate of Fourier transformation of the second signal. See, R12 of tau, the Fourier transformation is x1 of omega and x2 star of omega. x1 of omega and x2 star of omega. This is known as correlation theorem. Correlation theorem. So actually, when the two signals are convolution, what is the frequency domain? The frequency domain is in the product of x1 of omega and x2 of omega. But the cross correlation function R12 of tau, the Fourier transformation is x1 of omega and x2 star of omega. x2 star of omega means one signal is a Fourier transformation and another signal is a complex conjugate of Fourier transformation of the second signal. This is known as the correlation theorem. Correlation theorem, my students. Okay. Now take the second one here, the correlation of power signals. These are energy signals we completed. Now the power signals. Same formula you have to use, but the R12 of tau is with 1 by t, the integral t minus t by the t by 2. The cross correlation function R12 of tau for two periodic signals x1 of t and x2 of t may be defined with the help of average form of correlation. If two periodic signals x1 of t and x2 of t have same period at t, then the cross correlation is defined as cross correlation of power signals is defined as 1 by t, the integral minus t by the t by 2, or integral t x1 of t and x2 star of t minus tau dt. Then the two signals x1 of t and x2 of t are orthogonal signal, then this is cross correlation orthogonal signals is a 0. Okay, my dear friends, the power also is a 0 only. Another form of cross correlation between x1 of t and x2 of t is defined as R21 of tau is equal to R21 of tau is equal to x2 of t and x1 star of t minus tau dt. And these two are not equal, my dear students. When it is equal, when we can take it is R21 of minus tau only, so both are equal. Okay. Another form of the cross correlation function between x1 of x2 is defined as this equation. So the power signal is 1 by t into integral minus t by the t by 2. The same thing, x2 of t and x1 of star of t minus t. And some of the properties of the cross correlation of the periodic signals, the power signal also, that power signals is first property is the Fourier transform of cross correlation of two signals. The Fourier transformation of cross correlation of two signals is equal to the multiplication of Fourier transform of one signal and complex conjugate of Fourier transform of another signal. Same thing, my students, as in the properties of energy signal, in the power signal also R12 of it is the Fourier transformation is x1 of omega and x2 star of omega. And the second property is also saying that when tau is equal to 0, the cross correlation function is a 0, but it is a power p. There it is a power e. That is limit t tends to infinite 1 by t the integral minus t by the t by 2 x1 of t x2 star of p dt is equal to 0. So here it is tau is equal to 0, it becomes of x star of t minus 0. Then the signals are said to be orthogonal over the entire time interval. The power signal p is equal to R12 of 0 at tau is equal to 0. Okay, my dear students, you can write this one as a p is equal to power signal p is equal to R12 of tau at tau is equal to 0. Nothing but the power is a 0 here. Otherwise, in the energy signal, energy is equal to 0. R12 of tau at tau is equal to 0. In the energy signals, cross correlation of energy and the cross correlation of power signals. Two properties is similar to the power and the energy. And the third property also, the similar see, the cross correlation exhibits conjugate symmetry. R12 of tau is equal to R21 star of minus tau minus. R12 of tau is equal to R21 star of minus tau. And I'm interchanging these two functions, but here the not the tau, it is a minus tau minus tau. Unlike the convolution, the cross correlation is not commutative. Only the convolution is commutative, but correlation is not commutative. So R12 of tau is not equal to 21 of tau here. When it is equal, whenever we can take the minus tau only, both are equal. Following, my dear students. Okay. And these, whatever we discuss the properties, in the tomorrow's class, we can see the proof of R12 of tau is equal to R21 star of minus tau. The cross correlation exhibits conjugate symmetry. Conjugate symmetry, the property. What we are discussing about the property statements in the cross correlation of power signals and energy signals, both are the same here. Okay, when tau is equal to 0, R12 of 0 is equal to 0, and the two signals in the frequency domain, the Fourier transformation of cross correlation. One is a Fourier transformation, another one is a complex conjugate of the Fourier transformation. Okay. In the tomorrow class, we can see the examples of cross correlation. Okay, my dear students, examples of cross correlation or the proof. So one of the proof here. Okay. So any doubts? Please raise. Okay. Thank you.